I'm hoping. All right, so exponential functions, they basically look like this, where you have a number raised to a variable this time. Okay, until now we were talking about polynomial functions where it was the opposite. It was a variable raised to a number. Now it's the opposite. So 4 to the x, 1 over 3 to the x, 7 to the negative x, all are examples of exponential functions. Here are some more. Another one is e to the power of x minus 1. Remember, e is just a number. All right, so here's how graphs of exponential functions look. Imagine you are hanging out with a friend who has strep throat. They have some sort of, a bacterial infection. And, after a while, this is in the morning, and then by lunch, you know what, you feel a little something in your throat, whereas you were perfectly fine in the morning. By the time you go home, by 4 or 5, you are just completely done with. Okay, you can barely move, you're completely sick, you're coming down with a fever. So what happened? When the day started, you were feeling completely fine. All of a sudden, you got a couple bacteria on you from your friend, and within minutes, hours, they multiplied and they grew exponentially. So now, you're just completely overcome with bacteria. So whereas you had very few in the beginning, now you've got trillions of them in your body. And it happened very, very quickly. This is characteristic of exponential growth. Okay? Where something increases very, very rapidly. And then you go to the doctor and he prescribes some antibiotics. You start taking the antibiotics, and you know what? Within a day, you're already feeling so much better. So all that bacteria just died off immediately. Okay? So exponential growth and exponential decay. In one case, something is multiplying rapidly. In the other case, something is decaying very rapidly. And if you just take a look at the graph, so for example, if you're at this point on the x axis, and if you go over just a little bit, just this much, okay, look at how much you've increased in the y, okay? So just by going over a little bit on the x, you have a huge increase on the y. This is a characteristic of exponential functions, okay? All right, so what do exponential functions look like? The domain is all real, so you never have to think about this. The domain for exponential functions is always, always all reals. The range, however, is 0 to infinity, and that's because exponential functions always have an asymptote at y equals 0, okay? The y-intercept is always 1. Asymptote is the x-axis, so look at the end behavior. As x approaches positive infinity, this is clear, you're going up to positive infinity. But as you approach negative infinity, here, your graph approaches a value of what? 0. Okay? And it's continuous. And for exponential decay, everything is the same. The only thing that changes is this. Okay? Where it's opposite. So as you go to positive infinity, your graph approaches 0. And as you go to negative infinity, your graph approaches infinity. All right. Now, what about, okay, so let's go here. How do we differentiate between growth and decay as far as the equation is concerned? So this is the equation for an exponential function. Everything rides on this base b. If b is a number greater than 1, we call it growth. If b is a function between, if b is a number between 0 and 1, so for example 1 over 4, 2 over 3, 5 over 7, then it's exponential decay. Okay? B can be negative. It doesn't matter. We'll talk about that later. So this should be absolute value in that. Okay, so you just take the absolute value of it. And if it's a fraction less than 1, then it's decay. So look at this one. Let's classify these. Is this growth or decay? Growth. What about this one? It's 0.5 to the power of x. Decay. What about this one? Decay. And this last one? Y growth. Exactly. So this is 1 over 4 to the negative x, which is 4 to the positive x, so it's growth. Okay, so let's graph functions here. I'm going to show you how I would like for you to do it, and if you just stick to it, it's just, the same thing throughout, okay? The first thing you want to identify is the asymptote. Now, for the default function like this one, the asymptote is going to be y equals 0, and I'll talk later about when that changes. The y-intercept is when you have 2 to the 0, so it's 1, so we say 0, 1. Now, is this function one of growth or decay? Growth. When you have a function of growth, always pick these values to plot. So -1 to 2. I've found that this is very convenient because anything smaller or bigger gives you numbers that you can't really manage. All right, so here we're going to plug them in. 2 to the -1 is a half. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. The first thing we want to do is put in our asymptote. Okay? So, and then we plot points just like we always have. So at -1, we're at a half. 0, 1, 1, 2, 2, 4. And this is how it looks. All right. I would like to see your function like this. So remember, you're not playing connect the dots. You're not going to go from this dot to that dot. I want to see you following the asymptote on this side, and I want to see you going up on this side. Okay? All right, the domain is negative to positive infinity. The range is 0 to infinity. End behavior. As we go to negative infinity, f of x goes to 0. As we go to positive infinity, we go to positive infinity. And it's continuous on its domain, negative infinity to positive infinity. The domain of exponential functions is never, ever, ever anything other than all real. All right? So you don't even have to think. All right?
Can we just write the all real?
Yes. Nope. Okay. So here we have 3 to the negative x, which in reality is 1 over 3 to the power of x, right? So it's decay. The asymptote, regardless, is going to be y equals 0, and the y-intercept is 0, 1. For now, yeah. Okay, let's go down. Let's skip the graphing for a minute. Let's go down here to the domain. Because it's an exponential function, what's the domain? And the range? 0 to infinity. So if this is decay, as we go to negative infinity, the graph is going to get bigger, so positive infinity. And as you go to positive infinity, it's going to decay to 0. So think of it that way. It's going to eventually decay to 0. And it's continuous anywhere on its function. And the reason why I did it like this is because, you can easily do this without a calculator. You can even graph without a calculator, okay? So, -2, when x equals -2, I have 3 to the power of negative 2, so it's 9. This is 3 to the power of 1, so it's 3. 3 to the power of 0 is 1. And 3 to the power of minus 1 is 1 over 3. Okay, so let's graph. As x equals negative 2, we're at 9. At x equals negative 1, we're at 3. 0, 1, 1, 1/3. All right, so here we have this one, the asymptote. On a test, you will have points earmarked for asymptote. So if you miss that, it's automatic points off. Top drawer. Asymptote. Okay. Now, transformations. Top. Transformations. It's the same exact situation as with any other function. All right? So, if you have something like this, okay, y equals 2 to the power of x plus 1, what does the graph do? It moves to the left 1. Okay, here, look at this one. We went from 2 to the x to 2 to the negative x. This is a, right, but what is it as far as transformation? It's a reflection around the y-axis. Which in the case of exponential functions also happens to be the difference between growth and decay. Okay? Question. I'm doing a screencast. Okay. Now, look at this one. Don't look at the graph. Just look at the function. You have 2 to the x, and now we're multiplying it by negative 3. As far as transformations, what is that? This is a reflection around the x-axis. Well, I mean, so you have both. You have a reflection and you have a vertical dilation. I'm just going to focus, hang on, I'm just going to focus on the reflection right now. Give me a second. Now, look at the blue one. Is it growth or decay? Clearly it's growth. What about the red one? No. It's still growth. Why? It's negative growth. Okay? Growth essentially means as time progresses, things get bigger. The numbers get bigger. So when we're talking about bacteria, it's very clear that here the top one is growth because you've got lots and lots of bacteria as time progresses. Let's talk about the debt. When you owe money, you're in the hole, you're in the negatives, right? So 20 years ago, right, or 20 years ago, our debt was what? A couple billion. And then over like 8 years after the whole war thing, it went into the trillions, right? So whereas we owed this much money, then immediately we owed that much money. What happened to our debt? It grew, okay? It grew into the negatives. So both of these are growth. In the case of decay, In the case of decay, now this is clearly decay. As time progresses, you decay to 0. And the negative of decay, as time progresses, decays to 0. Okay? So your debt will decay to 0. All right? So both of these are decay. Both of these are growth, and both of these are decay. So remember that decay, a characteristic of decay is you decay to 0. Okay? So my however many years of experience has taught me that this can be confusing. So make sure to nip it in the bud now. Okay? All right. Yeah. Okay. Natural base. You've seen the natural base before. It's a number called E. And this is an irrational number called E. Issues. Okay. It's an irrational number called E. So, how does it come about? It turns out that we see this expression a whole lot in math. Okay? 1 plus 1 over x to the power of x. It comes up in lots and lots of formulas, lots and lots of expressions. And a lot of times, we're looking at the end behavior of this function. Okay? So as it turns out, if you have this function, and if you look at the end behavior of it, if you graph this, it looks like this, where after a while it levels off. Okay? So if you check the end behavior, it turns out this levels off at this irrational number 2.71828 blah blah blah. Okay? It's always that. So, because this shows up all the time, they've come up with a special letter for it, E. Just like 22 over 7 is a ratio that shows up all the time because it's always the ratio of the diameter and the circumference of a circle. Because it shows up all the time, they have a special name for it, and it's what? Pi. Same thing for this, it's E. So E is an irrational number, the value of which is this. Okay, this is where E comes from. We'll come back to that later. So now let's graph E to the x. All right. E to the x is just like having 2 to the x, except we now have 2.718 blah, blah, blah to the x. So is it growth or decay? Growth. And again, it's going to have the same asymptote at y equals 0, the same intercept at 0, 1. Now, if it's an exponential function, what's the domain? Always. All real numbers, negative to positive infinity. And exponential functions, it's growth, whatever. It goes from 0 up to positive infinity. If it's a growth function, as x approaches infinity, y goes to, as x approaches infinity, y goes to infinity. And at negative infinity, we go to 0. And it's continuous on the domain. So all this without a calculator. Okay? It can be done. Now, for the graphing of E, you do need a calculator. All right. Again, we pick the same values, negative 1 to 2. So if I have e to the minus 1, we plug it in our calculator, and what do we get? Which is, I need the value of it. What's e to the minus 1? 0.36. Okay? Right, that's fine. It's just for plotting purposes. So e to the 0 is 1. E to the 1 is 2.7, 2. And e squared, 7.4. Okay? All right. So asymptote is here. E to the minus, so when x is negative 1, we're here. X is 0, we're at 1. X is 1, we're at 2.72. X is 2, we're at 7.4. So here. There. Okay? All right. Now what happens here? What does the plus 3 do? Up 3, because it's not with the x, it's afterwards. Okay? Now, on a normal exponential function, where is the asymptote? At y equals 0, the asymptote. Here, the asymptote is going to move up 3 spaces to 4. Okay? So asymptote to 3. Asymptote also moves up 3 units. The y-intercept, it used to be 1, it's now 4. Okay? The 2x is going to make it a little bit steeper. Okay? Right. Okay, so to graph this, here's what we're going to do. You are going to graph 2 functions. First, I graph everything until here. Okay, e to the 2x. That's what I have in my chart here. So, again, because it's growth, I go from negative 1 to 2. So here I have e to the negative 2, e to the 0, e to the 2, e to the 4. So here, e to the 0 is 1. E to the 2 is 7.4. What's e to the negative 2? Later. What's e to the negative 2? So 0.14. And e to the 4 is a large number. How much? Okay. So first I'm going to graph this one. This is going to be my, sort of my modified parent function. Okay? So when x is negative 1, we're at 0.14. This is for the original one. And then at 0, we're at 1. At 1, we're at 7.4. I'm sorry. Yeah, sorry. And at 2, it's way too big. So here, this is my function. Now, the new one, so this is e to the 2x. The other one has a translated asymptote at 3. So the y-intercept is 4, and each other point moves up 3. So it's going to look like this. And this is y equals e to the 2x plus 3. Up. Okay.
Do you have to, like on a test or case, do you have to graph it?
Both, yes. Okay, so the domain, it's an exponential function, so you don't even have to think. It's always all reals. But the range of this new function is what? From 3 to infinity. Okay? And you can tell that from the equation, right? Because it's going up 3, so it's from there. As x approaches negative infinity, we go to 3. As x approaches positive infinity, it's infinity, and it's continuous everywhere on its domain. Okay. Exponential growth and decay. So applications of this are everywhere. The first is in compound interest. This is when you go to the bank, you deposit money in a bank, and if it's simple interest, right? If you borrow some money from somebody, if it's simple interest, it's basically like if you have a 5% rate, at the end of the 3 years, you just say, okay, 5% of however much I borrowed, here it is, there we go, okay? Compound interest, suppose it's a 5% rate, and you put your money in there for 3 years, but you don't just get paid one time at the end of it. You get paid throughout the term, okay? And depending on the type of account, you can get paid once a year, or the bank might pay you interest quarterly, so 4 times a year, or they pay you every month, okay? That's compound interest. And this is the formula. I know you've seen the formula before. It's similar. So this is, okay, we're going to get to that. You did this too. This is the principal. So P is the principal. R is the rate. N is how many times a year you are getting paid money. So if you're getting paid money monthly, N is what? 12. Okay? And A is the balance. So when you get your statement, that's how much money you have in the bank at that time. T is years, time in years. Okay. 12 is N. N is the amount of money you get paid. So let's talk about this one. So someone invests $2,000 into an educational account for her daughter when she was an infant. The account has a 5% interest rate. If she does not make any other deposits or withdrawals, what will the balance be after 18 years if the interest is compounded quarterly or daily? Okay, so quarterly is the bank pays you every quarter, so 4 times a year. Okay? All right, so the principal here is $2,000. The interest rate is 0.05, must be in decimals. This is where students make a lot of mistakes. Time is 18 years. And what we want is A, the balance. Now, for part A, quarterly means N is equal to 4. So we plug it into the formula. A is equal to P, 1 plus R over N to the power of NT. This is 2,000. 1 plus 0.05 over 4 to the power of 4 times 18. And we're going to plug this in the calculator all in one shot.
Where's the 1 from?
The formula. It's 1 over, it's 1 plus R over N.
All in one shot?
Yeah. Well, I actually have it here. This is it, okay? All right, so do you see how it's 2,000 times 1 plus 0.05 to the power of 4 times 18. So equals, this is how much money she gets at the end of it. 4891, right. And I will not tell you what to round to because you need to know that when we're talking about money, you have a dollar sign, and it's gonna go to 2 decimal places for dollars and cents. Now, there is another account. There is another package where, you know, the bank employee basically tells her, hey, you know what? Invest in this, because here, rather than the bank paying you 4 times a year, they're paying you every single day. So the woman says, oh my God, I'm going to be rich. Okay? So let's see how much rich. So N equals, if it's daily, how much is N? 365. So now A equals 2,000. 1 plus 0.05 over 4 to the power of 360. Sorry, hang on. It's over 365 to the power of 365 times 18. And, you know, you just modify your entry in the calculator here to this. You can do second, enter, and it brings back the last equation, and you could just go and edit. So she got paid now $4,918.90. So over the 18 years, how much more money did she? Right. Okay. So she goes to another bank, and they say, hey, forget about that one. They're only paying you 365 times a year. What is that? We can have our computer programmed to pay you every nanosecond. So continuously you're getting paid. So how many times a year will that be? An infinite. So what was the formula we were using before? So now, listen, rushing. As n approaches infinity, let's take this one. What does this look like? E. Okay? Remember what we had before, 1 plus 1 over x to the power of x? Okay? If n is infinity, then this is E. Now, you also have an R and T in there. We don't want to talk about how that factors. So if this is E, you then reshuffle the R and the T. Too much math for us to go into in this class. So it becomes this one. So that becomes E, and you just, you know, toss in the R and the T. Okay? So it's PE to the RT. I call this the Purdy formula. Okay? So this is used for compound interest when it's paid continuously. When you see the word continuously, compounded continuously, you just know that this is what you're going to use. So this poor lady, now she has this new account. Okay, this bank promises to pay her infinitely throughout the 18 years. So A is 2,000, E to the power of 0.05 times 18. How much money does she get at the end of it? Anybody? So 4,049.20 cents. So compared to her being paid 365 times a year, how much?
30 cents.
She makes 30 more cents over the 18 years. Right. Okay. Okay. In addition to investments, other topics also rely on exponential functions. Okay? Examples are populations, whether it's people or animals, populations of people, animals, or bacteria, radioactive material, okay, all change at an exponential rate. Now, for that, we use similar formulas, okay? So, this is one formula. This is used, hang on, this is used when something changes on a yearly basis. And really, this is the same formula as the one we were using before for the interest with n equals 1 because it's annual, okay? Now, this book uses this notation. I, however, use another notation, which is y equals y naught 1 plus r to the power of t. And I said that wrong. It's not just me. It's everywhere else. Okay, this is a more common way. In fact, this is the one you're probably going to run into in calculus next year. Now, if something changes continuously, like, for example, radioactive decay, okay, then we use this one, and the more common form of it is y equals y naught e to the kt. Now, we use one formula for growth and decay. However, if it's growth, r is positive. If it's decay, r is negative. Here, if it's growth, k is positive, or for decay, k is negative. Yes? T.
And then also, this population is their path. Because there are only so many people that exist.
So, there are so many factors. We're just taking a...
Like, theoretically, we could forever keep, like,
People produce it, are they producing?
Okay, that part is not what we're talking about right now. I have... Okay. We need to finish. So a state's population is declining. That means this is decay. At a rate of 2.6% annually. So if it's decay, then the rate is negative 0.026. The state currently has a population of approximately 11 million people. So this is the current, why not? It's the current initial amount. If the population continues to decline at this rate, predict the population in 15 years. Okay. So, the formula that we're going to use is the first one, right? Because this is an annual decrease, okay? And it says so here. So it's going to be y equals y naught e, I'm sorry, not e, 1 plus r to the power of t. So it's 11. No need to put the whole million. 1 minus 0.026 to the power of 15. Okay? So this is 11 times 0.974 to the power of 15. And when we plug that in, how many? 7.4 million in 15 years. Now, one more thing I have to say. Sometimes the book or the test question will ask you for a model. All right? The model is basically this, but with the t as a variable in there. So it'll be y equals 11, 0.974 to the power of t. Okay, so that's the model. Okay, yes.